we will now look at the practical detail about cache coherence protocols. And I have said that if a processor wants to modify a variable, but what actually happens is that we use this cache blocks. I mean, the data item that is kept coherent is not only one variable, but for instance, 32 or 64 bytes at a time. So when one CPU wants to read a variable, it not only fetches that variable, but it fetches 32 bytes. The 32 bytes where that variable is located. Okay, so you take the address and divide it by 32, and then you get the block number, and it is that block which is fetched. So it's not the variable plus, I mean, including the next 32 bytes. It is a block which is of a certain size. Okay, so the cache coherence protocol has a state for each cache and memory block. And for the cache, it can, for instance, be these 4 states: shared, invalid, exclusive, and modified. Okay, so what do they mean? Shared means that this cache and possibly some other cache have another copy. It's not certain that the others have a copy, but at least this is a read-only variable for the time being. I mean, if the processor wants to modify this variable, I say variable, but I mean cache block, then it has to request write to modify it. So how could it be that only one cache has it in shared state? Shouldn't that be exclusive? Well, it could be that 2 CPUs have it in shared state, and the other decides to remove that data from the cache and store something else. Then it's no point in telling all others that they have removed their copy, because usually it will not affect them. Okay, invalid, if it has been removed due to a write request by some other CPU. Exclusive, well, that means only this cache and the memory have a copy. So it's fine to modify this cache block, since no other cache has a copy. And if it actually has modified it, then it will get the state modified. So why have 2 different? Well, when this cache block is going to be replaced and some other data is put in the cache, then if it is modified, then that cache block must be copied back to the memory. But if it's only exclusive, then there's no point in copying it, since the memory already has a copy. So it's useful to distinguish between these. And there are similar states for the memory block. And in addition, a bit vector with the information about which caches have a copy. Also, the memory block can be in a transient state when acknowledgements are being collected. Okay, so the memory access penalty, that is the time that the CPU has to wait for the cache to get either ownership or a copy of the data when it wants to read it. And the memory access penalty for reads, they are much more difficult to avoid, since usually the CPU has nothing else to do than wait until it gets the data. And it doesn't matter if it's sequentially consistent or a relaxed memory model. So that is tough to avoid. There are approaches. For instance, one can prefetch the data if one is more or less certain that it will be useful, so that it is copied into the cache before the CPU gets a cache miss. That can be good, but there is a risk, namely that it will replace some data that we still need to use, and then it becomes slower. Okay? And obtaining the exclusive ownership of data is one of the main disadvantages of sequential consistency. I mean, waiting for that. And how significant this is, it depends on the application. And just to be, so there is no misunderstanding, as soon as the cache has the data in modified or exclusive state, then it is free to write to it at once without asking the memory controller. Since that's the main idea with having these states. So now that cache is the owner of the block and can write to it as much as it wants. So if it gets ownership and wants to write to a certain cache block 1,000 times, it just does that locally. For a write update protocol, it would have to send 1,000 updates, which would result in numerous requests. Maybe writing to something 1,000 times is not the most frequent thing to happen, but it's really disturbing for a programmer to think how much will this create noise in the machine, instead of thinking that now I own it and now I can write to it as many times as I want. So write invalidate is better for the health of programmers, in some sense at least. Okay, so how can we optimize sequential consistency in hardware? Well, data prefetching, that can be done by the machine. And for instance, the Power 8 machine that we have in the course, it does data prefetching automatically. There is also software initiated data prefetching, and that can be done also in exclusive mode. The automatic hardware initiated prefetching is only done in shared mode. It's a little bit too risky, not for correctness, but for performance, to do data prefetching in exclusive mode, since that is basically, not only basically, but it will invalidate other copies. And if the CPU which did this actually didn't need the data, then it is a big risk that it has created cache misses. Okay, another thing that can be done is for the cache coherence protocol to observe how a certain cache block is accessed. For instance, if it's first read and then modified and then not accessed again. And if this occurs repeatedly for different CPUs, then the cache coherence protocol can determine that, okay, there is a read and write sequence here. And it can give exclusive ownership directly instead of first requesting, granting shared state and then forcing the CPU to request ownership of the block. So when can this happen? Well, when different threads update a certain variable, then this will occur. And actually, in one conference that I attended, there were 2 papers presenting essentially the same cache coherence protocol. So they both research groups had invented the same protocol, and it did exactly that. Okay, for superscalar processors, one can permit speculative execution of reads, and then if there later comes an invalidation request, then that instruction can be ignored, and subsequent instructions which use that value. Okay, for those of you who have taken efficiency, it's nice to know this last point here. But if you have not taken this or don't know about superscalar processors, don't worry, because I will not ask anything about that, since it would be unfair. But it's very nice to know that this option exists. Okay. Can we optimize sequential consistency in the compiler? Well, one could imagine that there is a memory read instruction or load instruction which also requests ownership. And then sometimes optimizing compilers can determine that some object, such as this P, will have, well, it's not necessary to have all 3 attributes being incremented. It's sufficient with 1, but it demonstrates more clearly that we want to modify some attributes in this object that P points to. If this is Java, otherwise there would be an arrow if it was C. And how can the compiler determine this? Well, it's easy by doing a data flow analysis and connect the write and the read. And as a matter of fact, when an attribute or field in a struct is updated like this, it will be a very local search. I mean, this information is it's only a few instructions between each other, so it's very trivial. Actually, it's very effective just to look at what happens in the same straight code sequence, but by doing data flow analysis between so-called basic blocks or parts of a function, it will be somewhat more efficient. Disadvantage of this, of course, is that it would need new instructions, namely 1 for each basic data type. So, summary of sequential consistency. The 2 requirements of sequential consistency: program order of memory accesses and write atomicity. So, while this is nice because it makes it easier to think about parallel programming, it has drawbacks. First, these 2 requirements, and then the effect of this. Namely to limit compiler and hardware optimizations, and therefore introduce, well, not only that, but also introduce write access penalty. Since when the CPU writes to a cache block for the first time in some part of the program, it has to wait until that write has completed, and then it can continue with other accesses. Okay, so this is most important for writes, since reads are equally difficult for relaxed memory models as well. Okay.